Moura, and she will talk about the Vortex-Wave System with a finite number of vortices as the limit of the Euler-a model.
First of all, I'd like to thank the organizers for the opportunity to give this talk. This is a joint work with Milton and Helena Lopes. We're all now at UFRJ. So I'll first start giving an outline of my talk. So the Vortex-Wave System is a mathematical model for two-dimensional incompressible fluids in which you have a continuously distributed vorticity interacting with small regions of concentrated vorticity. So in this talk, we'll be considering solutions of the 2D Euler-a model when the initial vorticity is the superposition of a finite number of point vortices and unbounded vorticity. And we are going to show that as alpha tends to 0, these solutions tends to a solution of the vortex-wave system. So I'll just quickly start with the Euler equations in RD. As we've seen before, this is just to introduce notation. Here my V is the vector field of the fluid, P is the pressure, and we have that my velocity field is divergence-free, which reflects the fact that my fluid is incompressible. In our analysis, it will be extremely convenient to be working with the vorticity. So the vorticity, as we've seen, is the curl of the velocity field, that in R2, it is a scalar quantity. So in this, if you take the curl of the Euler equations, we'll obtain in R2 that the Euler equations can be written as a transport equation for the vorticity, where we can recover our divergence-free velocity using the two-dimensional Biot-Savart law, where here my K is the curl of the fundamental solution of the Laplacian equation. So the importance here, as we've seen before, that the difference between the vorticity equation in R2 and in R3 is that we have that the vorticity is transported by the flow. In this talk, we're particularly interested in a special kind of measure-valued vorticity. So more precisely, we're going to define M to be the space of all finite real Hadron measures equipped with the total variation norm. And we'll be interested in the mixed problem in which the initial vorticity Q0 is of a particular type. We'll suppose that our initial vorticity is the superposition of a finite number of point vortices centered in x1 to xn with intensities m1 and mj, and a non-atomic background vorticity omega 0 that has compact support, and we'll be assuming that it belongs to LP with p bigger than 0. As we can see here, of course, delta x minus xj is the Dirac measure centered on my point vortices. We have that Q0, it's singular in each of our point vortices, so it's not clear how can we make sense of Euler solutions with these types of initial condition. So in order to treat these incompressible fluids in which you have a continuously distributed vorticity interacting with small regions of concentrated vorticity, such as in the problems of a hurricane motion, Marchioro Povirenti in 1991 introduced the vortex-wave system. So this model separates the evolution of the background vorticity omega that evolves using by the Euler equation from the evolution of my point vortices Zi that evolve through the point vortex system, and these two equations are coupled by means of the Biot-Savart law. So it's clear that if my background vorticity omega is identically 0, we recover the point vortex system. So we call a solution of the vortex-wave system a background vorticity omega together with the vorticity trajectory Zi's. This term here in blue is the velocity associated with point vortices with mass mj that travel along the trajectory zj. So we can see from here that the evolution of point vortices, they evolved, they're moved by the background velocity associated with the background vorticity, as well as with the velocity associated with the other point vortices. On the other hand, we have that the point vortices influence the flow of the background vorticity. So I will not talk a lot about the existence and uniqueness results because Milton will be talking about the vortex-wave system in more detail this afternoon. I just want to point out that Marchioro Povirente in 1991 proved the existence of Lagrangian solutions for the vortex-wave system when they're imposed that their initial condition omega 0 belongs to L1 intersect L infinity. The point here is that these Lagrangian solutions introduced that Marchioro Povirente used, they're extremely strong notions of solution since they require the existence of a continuous in time and space flow. So in this talk here, we'll be focusing on a weaker notion of solution, which is the Eulerian solution. So we will, given an initial vorticity omega 0 in L1 intersect LP, and our point vortices x1 to xn with intensities m1 and mj, we'll say that this is an Eulerian solution of the vortex-wave system if omega is an L infinity in time, L1 in LP in space. Our vortices trajectories are in L infinity, and they satisfy this system in the sense of distribution. Here, V is obtained with a convolution with the Biot-Savart law, and my curly K is simply the sum of these velocities associated with the point vortices. What I would like first to note is that in order to be working with Euler solutions, we need to make sense of this product here, omega V and omega curly K. Yes? So if you suppose that your omega is in LP, or omega T is in LP for P bigger than 1, in order to make sense of these products, it's interesting to note that we know that our curly K is now Q log with Q strictly smaller than 2. Therefore, in order to make this, this product curly K omega locally integrable, we need that our P is strictly bigger than 2. And in this case, if P is strictly positive, is strictly bigger than 2, we can show that our velocity V is uniformly bounded and continuous in space, and therefore our product V omega is also locally integrable. Therefore, it makes sense to be looking for existence of Eulerian solutions for the vortex-wave system when P is bigger than 2. And this is exactly what Hélène and Milton Lopes, together with Evelyne Miot, have shown in 2011. So under these conditions, they've shown that there exists a global weak Eulerian solution of the vortex-wave system. What are we going to present in this talk? We're going to show that we can obtain a Eulerian weak solution of the vortex-wave system as a limit, as alpha tends to 0, of solutions of the alpha Euler model. So the alpha Euler model, the 2D Euler alpha model. So the Euler alpha model was introduced by Holmes, Marsden, and Hatu in 1998. The alpha model is an inviscid regularization of the Euler equation, where we have that the vorticity satisfies this system here, and we have that here, my U alpha is the filter velocity, W alpha is the filter vorticity, and as in the Euler equations, we have that our filter velocity can be recovered from the vorticity using a convolution with now a smoother kernel K alpha. I'll discuss, so my kernel K alpha has this form here. It is the grad perp of this function psi alpha that is of this form here, where k is 0, is the modified Bessel function of second order, of order 0. So in 2001, Oliver Scholar showed that if you that the 2D Euler alpha model is globally well posed when you consider initial data that are in the space of finite Hadron measures. Moreover, they were able to show that there exists a unique flow map that describes the evolution of the particles that preserves the Lebesgue measure. Therefore, it follows from the existence of this flow map that the vorticity is transported by the flow. So in particular, we can show that so it follows from Oliver Scholar's theorem that if our initial vorticity has this form here, is the sum of point vortices together with a bounded background vorticity, the vorticity, background vorticity belonging to LP, it will remain of this form for all t. And in particular, we have that it will follow from the fact that the vorticity is transported by the flows and we have a divergence-free velocity, that the LP norm of the background vorticity omega alpha are conserved, and that the signs of the intensities MJs are also preserved. And finally, we have that since Oliver Scholar's theorem guarantees uniqueness of solution, when we have time reversibility of solutions, we have that vortices cannot collide in finite time. Okay? So before we state our theorems, I would like first to discuss what is this Euler alpha kernel. So in this regularization, the singular kernel of the Euler equation is smoothed by means of a convolution with the green function G alpha, which is associated with the Helmholtz operator. We have that for each alpha, the kernel J alpha belongs to L1 and decays exponentially at infinity. So using the property that G alpha is actually radially symmetric, we can show that our smooth kernel K alpha have the same symmetric properties as the Biot-Savart kernel K. So using these results, we are able to show a few properties of the Euler alpha kernel. First of all, using the exponentially decay of G alpha, one can show that the kernel K alpha behaves at infinity, just as our kernel K. And moreover, we can show that the families of kernels K alpha converge uniformly to K on compact sets away from the origin. And also we can show that if you have a function G that is defined as the convolution of K alpha with F in L1 intersect LP, then we have that G is Holder continuous. Using these results, and in particular using the fact that it follows from Oliver Scholar's theorem, we have that they have that a unique flow map that preserves the Lebesgue measure. We are able to show that there exists a generalized Hamiltonian that we've defined to be this quantity here that is conserved in time. And using these results, now I'm able to state our main theorem. So we've shown that if P is strictly bigger than 2 and omega 0 belongs to LP with compact support or in L1, then there exists a subsequence of solutions of the Euler alpha model with our initial condition that converges to a global Eulerian solution of the Vortex-Wave System. And as in Milton and Elena and Evelyn theorem, we have that without the single sign condition of intensities, we obtain convergence on a closed interval. So in order to show our theorem, just first a sketch of the proof. Our arguments are based on their paper. We'll be considering the initial vorticity of this form and the resulting global solution given by the Oliver and Scholar's theorem. First of all, we're going to establish some uniform estimates with respect to alpha. to obtain compactness and obtain a weak limit. And at the end, we're going to show that our weak limit is a weak solution of the Euler-a model. So our uniform estimates. This is a result that it just follows. It's the same result that you would obtain with K alpha, with K instead of K alpha. So if our vorticities in L1 and L1 intersect LP with P strictly bigger than 2, one can show that since our omega alpha is transported by the flow that preserves the Lebesgue measure, we have that omega alpha is L infinity in time, L1 intersect LP in space. And moreover, using Young's inequality, one can show that V alpha is uniformly bounded in L infinity. So finally, using just as Marchioro Pulvirenti suggested, if we consider the moment of inertia, we are able to obtain a control on the support of the vorticities and of the flow. And we can show that they grow at most linearly. In order to do this, we need the symmetric properties of K alpha. We'll need the fact that our U alpha is uniformly bounded, and also we'll need our sign assumptions on MI. And we obtain this control on the support of the trajectories. And finally, using both these results, in particular, using the fact that we have a generalized Hamiltonian that is preserved in time, we are able to obtain a control to control the minimum distance between the vortices uniformly with respect to time. With this result in hand, I'm sorry, this is just the details, but it will just follow by the fact that we have the Hamiltonian is conserved. And finally, using these results, we obtain our compactness result. So we are able to show that there exists an omega and trajectory zi's such that we have that omega alpha t converges weakly in LP to omega. We have that V alpha, our velocity, converges uniformly to V on compact sets, and our trajectories, Zi alphas, converge to Zi uniformly on compact sets. With this compactness result in hand, we are able to prove our theorem. So we just need to pass to the limit now. So it remains to show that our weak limit is actually a solution of the vortex-wave system. The first part is very easy. So using the item 2 and 3 from lemma 1, we are able to show this uniform convergence of the velocities on compact sets as alpha tends to 0, and therefore we have that our vortex trajectory satisfies the desired ODE of the vortex-wave system. Now we just need to show that our background vorticity satisfies this equation in the sense of distribution. Here just reminding that curly K is the sum of the the sum of the velocities associated with the point vortices. In order to show that, we'll follow very closely the argument in Lopes and Mio's result. What we do, we're going to introduce a cutoff function, yes, in order to neglect the point vortices where we have singularities. So in order to do this, we introduce these smooth radial cutoff function, which is identically 0 in a ball centered at the origin and radius half, and identically equal to 1 outside a unit ball center at the origin. Now, what we do is we're going to introduce a small parameter alpha, a small parameter epsilon, and we're going to denote chi epsilon, the scaling of this cutoff function, so that as epsilon tends to 0, for all q smaller than 2, we'll have that chi epsilon tends to 1 almost everywhere, and the gradient of the norm, the LQ norm of the gradient of psi epsilon tend to 0. Doing this, what we're going to consider for given any given any test function phi, we are going to define epsilon, phi epsilon, the product of our phi with the product of these psi epsilon i's, which are simply our psi epsilons just now translated and centered at the vortices. And we'll define this product here to be psi epsilon. With this test function phi epsilon in hand, what we want to show, therefore, that our background vorticity satisfies this equation here. What we have is the fact that our Q alpha of this form is a global solution of the Euler-a model for all alpha. Therefore, we have that omega alpha satisfies this equation here. And what we're going to do, we're going to use the compactness results that we've seen in order to show that we have the desired convergence. So what we use here, we use the fact that V alpha converges uniformly to V. Therefore, this term here, V alpha dot grad phi epsilon, converges uniformly to V dot grad of phi epsilon. Afterwards, we use the fact that by definition our phi epsilons vanishes at the union of balls centered at the point vortices of radius epsilon over 2. Since this test function is defined in such a way, and we have that our trajectories zi alpha converges uniformly to zi's, we have that this term curly k alpha dot grad of phi epsilon converges to curly k dot grad of epsilon. And finally, we use the fact that we have that omega alpha converges weakly in LP to omega, and therefore we obtain our weak convergence of the product of this term and converges to this term. And therefore, the last step, we just use the definition of our phi epsilon, and we let epsilon tends to 0. And therefore, using the fact that we have symmetric properties, and we've chosen our cutoff functions to be radial around the point vortices, and we have also the fact that given a point in the support of a grad of psi epsilon, we have that this distance is uniformly bounded below. We are able to show, and also using the uniform L infinity bound on the vorticity, and the fact that we have already shown that the point vortices satisfy the ODE, we have this bound on this expression here, and therefore, using Holder's inequality, we obtain that this integral here is bounded above by this whole expression. And finally, given our choice of cutoff function, we have that this expression here tends to 0, as epsilon tends to 0, and therefore, we are able to show that our background vorticity satisfies the desired equation. So, thank you very much.
Thanks, Eleonora. Any questions?
So we have the yes, we're supposing that there is a background vorticity, yes.
But suppose I take it 0, then you have, that's the original system, not the alpha system.
Okay.
Global existence or short-term existence, finite-time existence until the vortices.
So this follows from the Lopez and...
I understand, but in this case, wouldn't the point vortices have only finite time existence before they collide?
The collide.
Vortices?
No. The vortices.
All vortices are positive. Okay, so the same thing in this case.
Yes, exactly.
But for the alpha model, you don't need it to be full.
No.
Okay, that's missing.
Hold on a second.
I'm sorry?
If the unregularized system has solutions,
yes.
why do you regularize?
When am I regularizing?
Why are you regularizing by the Euler alpha? If the
I just want to
unregularized-
show like stability in respect to the Euler alpha model, which is numerically interesting.
Okay.
Any other questions?
So do you think it's possible to obtain some kind of convergence of the trajectories in L1?
That would be
Yes.
interesting, yes.
So,
I think so, but I haven't worked on it.
for almost every year.
Yes, because
Excellent.
we have a very strong result from Oliver and Scholar, and they have a unique Lagrangian flow map. So be interesting. They've shown in their paper, they've shown that there exists convergence, but to Marchioro Puvirenti is Lagrangian.
Which is too strong
Yeah.
for union. Okay. Thank you.
Any other questions?
So without the single time condition, you obtain convergence on a local
Yes.
time interval. But you get convergence as long as the limit solution exists.
Exists, yes.
Okay.
So it would be, I'm sorry, just a sec, it would be interesting, and we would like to understand exactly what will, because for the Oliver-Scholar theorem you have existence, global existence, so it would be interesting to understand what exactly is happening.
Let's see, I liked the talk yesterday by Gene Wayne, so it makes me think that, makes me ask the question, do you think there's a comparable result for the Euler alpha system? That the vorticity, that in 2D the vorticity would converge to the I forgot the name of the vortex, but
Aucine vortices.
yeah, the Aucine vortex, yeah.
I don't know.
I somehow think it's essentially dissipated. I mean, one uses the dissipation in an essential way. So if you,
No, yeah, exactly. So, yeah, you
Oh, so
just
it
have
would-
transport. For no, yeah.
All right. Thanks again, Eleanor.
Right.
Our next order of business is a short course by Gene Wayne.